right? This data is not mine. This data is actually Intergovernmental Panel on Climate Change 2017 international data. Now you see that 28% is energy industries, means these energy industries actually they are converting, say, from fossil fuel to electrical energy, and they emit 28% of the total share. And the second position is the transportation, which is 23%, right? Which is 23%, right? The others are actually like, say, household, 14%, and then manufacturing industries, 11%, like that. Industrial process and products, they are 8%, agriculture, 10%, like that. But the second highest is the transportation. Now, transportation, actually, you see a lot of vehicles, they move here and there. Say, you find lorries, you find buses, you find various things. Okay. So then you see, if we can do something that can, I mean, reduce the greenhouse gases as well as it uses green energies. So twofold advantages we will get. First of all, first advantage is that stock of the fossil fuels which are diminishing, that will be saved. And second is that the greenhouse gases will be limited. So that is why we go for actually electric vehicles this day. Okay. And they are becoming quite relevant because of this reason, because transportation is carrying second highest emission of greenhouse gases in this atmosphere. Now we see the second slide. You see, now the technology, we will slowly move. Now, cutting edge research on EVs tends towards zero carbon electric vehicles, means we don't emit at all. Now, there are basically three techniques that are being, rather three categories of, say, EV technologies that are existing. First one is actually electric vehicles, battery electric vehicles, the category of electric vehicles I'm talking about, battery electric vehicles, the first category. Second one is, you can say, plug-in hybrid electric vehicles, or someone says even hybrid electric vehicles, right? Hybrid electric vehicles. And the third category is fuel cell electric vehicle. Now, their abbreviations are like this: BEV, PHEV, FCEV. Now, BEVs, their sources are solely dependent on batteries. Now, there is a debate, you can say, that you will always say that if the batteries we are using, then that can be easily charged from the normal grid. So in that case, it does not become a greenhouse thing. But if we charge the battery from the, say, non-conventional sources like, say, PV, wind, or some microgrid consisting of that, so then it becomes actually green energy, right? So we consider that only. We consider that battery being charged from the green energy. Second one is plug-in PHEV, plug-in hybrid electric vehicle. So actually here, hybrid means actually we have two options. We have actually, say, normal gasoline engine or normal petrol or diesel engine like that. And apart from which we will have electric drives. Both will be coexisting. Now there will be some management system that will decide which one to operate when. So this is one of the most, you can say, most researched areas. Now, fuel cell electric vehicles are solely actually powered by fuel cell. Now it is absolutely green, or you can say some small emissions can also take place, say hydrogen and all that there. So actually, you see that these are the three categories of electric vehicles that we see. Now, if you go for the configurations, we will go straight away from basics to the entire drive system, and then we will discuss regarding the battery management or battery state estimations. Now, you see that basic structure, you see, it is initially we had a pure gasoline engine, or you can say petrol, whatever it is. I mean, earlier name was gasoline. So it was the gasoline engine, IC engine, you can say. and then this is a transmission system, power transmission system. This drives the drive shaft, and then we have the wheels. Right? Now, the second category of electric vehicle or battery electric vehicle, we have a battery as a source. Then it will be motor or generator. Now, why we have written it motor or generator means actually it is a motor. Now, the conversion will be in such a way that supposing we are to brake the machine. So brake means actually the machine, the motor was in motion. So it has gathered kinetic energy from the battery energy, right? So now if we can convert this kinetic energy back to electrical and feed this to battery, so it becomes a regenerative type of drive system. So that is why it is written motor stroke generator. That means it will work as a generator during braking and work as a motor during normal operation. This is BEV structure, right? Now, if you see the BEV structure, so there are few configurations for battery electric vehicle. Now, this is first configuration. So yeah, we are only considering a four-wheeler system. So now you see that this is EM means actually electric motors. Now we can have in configuration 1 3 electric motors. That means two for the front wheels, and then one is for the back two wheels with a differential, and we have a common battery. Now these two arrows indicate that the energy can go from battery to the electric motor, and then it can come back to the battery when it is considered. So this is one of the most popular configurations for BEVs, battery electric vehicles. Now, second configuration is that we have a more flexibility, but coordination is a big problem, because here we can have 4 electric motors coupled to 4 wheels, and then battery is the common source. Then here coordination is a problem, but we can have nowadays DSP platforms that can operate very fast, and it can be controlled individually at tandem, depending on the driving situations, like say braking, turning, etc. So this is the second type of configuration of battery electric vehicle. And the third type of configuration is this one, where we have two differentials. The first differential is for the front wheels, and the second differential is for the back wheels. Now we have 2 electric motors only required here and a common battery, right? So these are the configurations on which the big companies are working, right? Say BMW or Maruti, even say Nissan, all those things. So I am not categorizing which one is working on which principle, but BEV is having these 4 configurations, these 3 configurations. Okay, so then the first configuration is the 3 motor configuration with the back differential. Second is 4 motor configuration with 4 wheels. Third is 2 motor configuration with 2 differentials on back and front wheels. Now the second is hybrid electric vehicles, hybrid HEV or plug-in hybrid electric vehicles. Plug-in means actually plug-in power. So PHEV or HEV, whatever it is. So now you see in hybrid system, as I have said, both the engines will coexist. That means here is a gasoline engine and a motor or a generator. They are coupled. So coupling is not shown here. And then there is a common transmission system that goes to the wheels. Now the motor and generator being powered by the batteries, and gasoline engine and all, they will be powered from the petrol or whatever sources we have, like say diesel, petrol, gas, gasoline, etc. Now you have a control system that will be deciding on that which one to operate with. So normally we have say battery drive, and say whenever large torque requirements is there, so there the gasoline engine can work because it can drive instantaneous high torque, right? So depending on working situations, the control system will decide as to which one to operate and when. Now you see the configuration wise. So this is the configuration 1 for the PHEV. Now you see here. So we have a fuel for the IC engine, right? And then it is a generator coupled, and then the a generator can drive a rectifier, right? Say, hello, some noise is coming. So is it someone's disturbed or not able to hear? Excuse me. So everything is fine?
Yes, sir. Yes, sir.
Okay, okay.
Yep.
So my voice
Everyone, please mute your
is
mic.
reaching you. Hello?
Participants, please mute your mic.
Okay, okay. So my voice is reaching you, na? That's all.
Yes, sir. Yes, sir.
Okay. So now see that you see here. So we have a generator. So we have a from IC engine. We have a generator. That means IC engine drives a generator, right? So that generator is actually providing the electrical power to the electric motor based on inverters or whatever it is. So then battery is as a backup. Now sometimes battery actually is working for the as an energy source for the electric motor. Now here all the energies are converted to electric energy, and then we have an electric motor. Now electric motor is driving this transmission system like the normal what we have in our cars, right? So this transmission is actually transmission differential is in the back wheels. So now this is the general structure. Okay, so IC engine is powering the generator. Now here we have an efficiency problem because a conversion efficiency is there from IC engine to electrical energy, and then that electrical energy is controlled by this inverter rectifier combination, and then it is going to the electric motor. Now if you see the second configuration, it is something a little bit different and little bit resembling what we in resemblance what we have shown in the basic block diagram just now. Now configuration 2, here we find that IC engine is being powered by the fuel, and it is directly driving the mechanical coupling or transmission system, right? And this is a better efficient system. Now battery is driving the three-phase rectifier and motor. Now what is happening now? This motor is battery can be charged from outside source. So it is not that always battery is charged from this IC engine. So here in normal situation, the battery will be driving, but for high torque conditions, the control system will react so that the IC engine can operate. And even sometimes simultaneously both can also operate. So there are various researches that have been going on regarding smooth transition of power from the IC engine to the electric motor, like that. Otherwise, the passenger will feel some discomfort regarding the transmission. Okay. So this is the configuration 2, and the configuration 3 for the configuration 3 for the PHEV is like this. Here we have IC engine has got common feature, like it can directly drive or it can even drive the generator. It is a better flexibility. It's the costliest kind of say configuration, where IC engine has a direct driving to the mechanical coupling, as well as it can drive to the generator. So there we can have a choice through our controller system, right? And then this generator will be driving the electric motor, and the battery is as a backup, or battery sometimes drives, or IC engine is as a backup. So actually this configuration is the costliest but most reliable. So we can have fail-safe operation, like say if your rectifier inverter fails, so directly the IC engine can drive. So if your IC engine fails, your battery can drive, right? So if your generator fails, either battery can drive or IC engine can directly drive. So all the combinations are existing. So you should be aware of the combination or your configuration. So based on which you can put up your research work or put up your say mechanical design, electrical design, etc. So these are the three basic, most popular combinations for this PHEP. Now for fuel cell FCEV, actually there is not much to be discussed, because it is not a very popular one. It is the very costliest one and very large cars, and their percentage is also less. I mean the configuration is same like BEV, battery electric vehicle, except that the power from battery is being taken, battery is replaced by fuel cell. That's all. Okay. So now if you see, if you want some comparative data, only thing is that greenhouse gas emission in the top row, greenhouse gas emission, battery EV and then PHEV, battery EV has the zero emissions. So fuel cell, FCV and PHEV, as I have said, there are emissions because when you can operate fuel cells, some low gases, some low gases in low amount, they can come out. And for HEV, of course, hybrid, whenever the IC engine is operating, emissions are there, but less, as because majority is by the battery. Now, and come to the cost. Now, cost, you see, highest cost is for the fuel cell, and then battery EV, and then PHEV is lower than BEV, but actually nowadays for large cars, plug-in PHEV is also having a good cost, comparable cost with that of battery EV. But the ratings are more. Normally, ratings for PHEV are more than the battery EVs. Okay. Now, major challenges, if you see among these three. Now, battery management and lifetime is the major challenge for the battery EVs. Whereas fuel cells, actually, they are not a very, I can say till now, they are not a very proven technology. Proven means rugged and proven technology. And now, fuel cells reliability, as I am saying, lifetime and infrastructure, all those things, they are under question. And plug-in electric vehicles are a choice, you can say, are a choice. Now, if you see that I mean, the demand, or you can say that the shipment means actually sale, you can say. The sale or the consumption, or you can say that preference by, say, the civilization or people. Now you'll see, now the data was from 2017, now 2018, 19, and 20 is saying estimated. So you see, we started this battery electric vehicle from here, actually, 2011, it is actually became slowly prominent. Now their PHEV compared to PHEV, BEV, battery electric vehicles ratio is much lesser, but PHEV is slowly increasing and still increasing. So, and FCVs are almost negligible. Say only 19 and 20 some estimation was there, but still we find that it is not very popular yet, as because the technology is having a large amount of cost as well as space as well as safety issues. So, so then the main competition is between the PHEV and BEVs. So usually, as I said, that BEVs are for small vehicles and PHEVs are relatively larger vehicles. Okay. Now come to the technologies. Now come to the technologies, means motor driving, motor characteristics, and then the converter techniques. So then electric vehicles, as I have said, they are not very new. I mean, we tried it from long back. But we didn't succeed simply because that controlling technique was not available for us. Good controlling technique. Good, as I am saying, good means fast response as well as accurate and reliable. Now, this has been made possible by mainly two things. One is that development of the electric batteries, development of the modern electric batteries, because you need to store the energy. I mean, store the energy in such a way that the energy per unit volume or energy per unit weight energy to weight ratio of the batteries should be high. Otherwise, it will happen that battery itself will become the load to the system, and the carriage, I mean, the load it will carry will not be significant. So this is one issue. And second issue, as I was telling, that controlling technique, that means this has been possible only with the advent of modern power electronic technologies, as well as the modern processor fabrication techniques. You see, nowadays, even 15 years back, people could not use microcontrollers or say to that extent as to what we are using now, because it has been made cheaper and easier for and easily available for everyone to use. First of all, you see microchip, microcontrollers. You see Raspberry Pi. Nowadays, even first-year students, they can program a robot and then they can run it. So how this has made possible? How this has been made possible? Because with the advent of the VLSI techniques and then modern research on getting faster processors. Now, earlier on 2000s and all, we used to have big processors such as Texas Instruments and all with difficult to program, which are difficult to program, the machine language and all. Nowadays, compilers are available. You can write easily programs in C and then load it. So all these things have made actually the development of the electric vehicle, rather electric vehicular technologies possible these days. So this has been mentioned here like this. The advent, rapid development in the field of power electronics and control techniques has created a space for various types of electric motors in electric vehicles. The same thing, right? So now we discuss the motor characteristics and then the drive system, right? So now you see that if you look at the basic categories of the motor to be driven,
Excuse me, sir. So, excuse me, sir.
Hello.
So, may I, sir, sorry to interrupt you. May I request you to put a presentation mode because we cannot see those slides properly. If you have presentation mode, we'll be able to see full slide.
Oh, sorry, actually, I have tried it. See, I'm doing it, but some issues are there. So I have gone it.
Now it's coming, sir. Now it's coming.
Okay, it's coming, no? Oh,
yes, coming now. Thank you. Sorry to interrupt you.
Earlier I tried, but it didn't occur. So okay. Thank you very much to point out.
Thank you, sir.
So now it is all right for you, huh? So it is changing. Slide is changing, and you are okay. Very good. So now you see, if you try to see the motor characteristics, that means once you want to know the drive system, you want to know the load that is trying to drive. That means the motor, the load, right? So now there are two basic types of motor characteristics available. Say one is this type of characteristics, which is known as soft characteristics, or this is known as series characteristics also. And the second one is the hard characteristics or stiff or shunt characteristics. So why we say soft characteristics and why we say stiff and why we say series. Series, as you know, it is resembling to the characteristics of series motors, DC series motors, right? And a shunt means actually it is resembling to the characteristics of shunt motors, right? Now, if you see soft, why it is soft and which one will be suitable to see? Now, soft means here, say, is the we have shown the speed torque characteristics, right? Now, if you take a derivative, say dtdn, right, or dndt, whatever it is. Now you find that dndt here for small change of speed, dt is very small. So you just try small change in dn. So the change in torque is small. Now, if you see the hard characteristics or stiff characteristics, if you change the speed to a very small value, say dn, so your torque change is larger, dn dt is larger. So what makes it different? Which one to use and which one is suitable for this drive system? Drive system means drive corresponding to this, say, transportation or corresponding to this vehicular system. So you see here, so I'll give you one example. So now, say supposing you are driving a car, right? You are driving a car. Now you have wheels, no, that are actually airs, that are having airs in the tubes, right? Wheels, airs in the tubes. So that air pressure is not constant always. So when the air pressure is low, let us say air pressure is low, so what is going to happen? Your effective diameter of the wheel will reduce, right? Your effective diameter of the wheel will reduce. Now, when you are driving a car, right? So your speedometer gives you which one? Kilometer per hour, kilometer per hour. And if you see how does it calculate? It calculates the RPM, right? So it senses the RPM. And then revolution per minute and multiplied by time. So it will rather revolution per minute, it converts to kilometer per hour. Linear. So now it does not sense what is the effective diameter of the wheel, right? So now what will happen? To have same linear speed of say 10 kilometer per hour, if the wheel diameter is less, its rotational RPM is more. Rotational RPM is more. So then if the RPM is more, so what is going to happen? Now in these characteristics, if RPM slightly changes, your torque is not going to change that much. But in the stiff characteristics, you see, if RPM changes slightly, your motor torque is changed very high in a high amount. So what is the harm? So then you have to exert more power, omega t. So power change is larger. So that is not expected from a drive system. So that is the major reason that we will be converting all the motor characteristics, whatever types of motor we use these days, to this type of series characteristics. So this is why we need series characteristics for our vehicular drive system. So now the types of motors that will be used, for vehicular drive systems are almost known to you, but still I will be repeating. They are DC series motors, brushless DC motors, permanent magnet synchronous motors, PMSM, and then three-phase AC induction motors. And last one is switched reluctance motors. So these are the various kinds of motors that are there, which can be used for vehicular drive system to operate under various conditions. Under various conditions, why I say after the discussion, you will come to know, right? So now you see the DC series motor first. Now DC series motor, people always know that it has got high starting capability, right? High starting torque capability. As you know that the series characteristics we have shown there. So near speed zero, we saw torque to be very large. So you come back here. So your speed zero is actually here. Your speed zero is here. So now you see the torque high. So how does it help you? Because all this vehicular drive starts with load. It does not happen that motor actually runs and then people rides the car. It doesn't happen, right? So all people ride the car and then it starts. So I mean, at starting, we require high torque capability of the machine. So that is why series motors are usually preferred. And the second type of advantage we get in DC series motors, that you see the torque characteristics. Torque is actually phi into Ia, proportional to rather phi cross Ia, and as phi and Ia they are perpendicular to each other, so we have phi into Ia. Sine of delta 90 degree, 90 is 1. Sine 90 is 1. So then you see this flux, as it is series, it is proportional to current. So effectively torque becomes proportional to current square of the current, right? Square of the current. So then with the help of smaller current, we can get larger torque. Means if we increase current by 2 times, right, the torque will be increased by 4 times. That's the major advantage we get. Another major advantage we get with DC series motor. And in case of shunt motors, you know, it is phi and Ia, it's a constant flux machine. So then 4 time torque means 4 time current. So usually armature has to be loaded to a very large extent. So that is not desirable. Now these are the stories when it was used, so I will skip it. Now then these characteristics make it ideal for now the drawback. The drawback. If you see the drawback, the main drawback of the DC series motor is its brushes and commutators that you all know. because brass and commutator, they require regular maintenance because there are deposits of carbon dust in the groove of the commutators, right? And when the deposit is high, so it can short circuit. Not only that, if the car runs in a hostile environment, like say where we have high humidity, right? Or we have some small say metal particles there in the air, say in the mines. So what will happen? Say that particles will deposit between the commutator segments, and it will make it short circuit. So this type of say unexpected thing should be avoided, right? Undesirable things, rather you can say, undesirable things should be avoided. So that is why that the usage of the DC series motors, rather the brassed motors, DC brassed motors, they are becoming lower and lower. Although you see that as a drive system, it is very easiest to drive the DC drives, DC motors. Okay. So then we will have a brief discussion only. So then we go for the brassless DC motors. Now brassless. Now by the name you see that we have no brasses here, brassless DC motors. So brassless BLDC, I think you have already read. So these BLDC machines are one sort of permanent magnet machines with trapezoidal EMF, back EMF waveform. It's trapezoidal back EMF waveforms. And since the rotor circuit, normally the permanent, there are various configurations. I will be coming to you because these BLDC machines have brought in the revolutions, have brought in the revolution in the electric vehicular technology. Say nowadays, a lot of bikes you are seeing. Now, not even nowadays, even 10 years back, 15 years back, you had seen it. But now it has become more because the motors are becoming cheaper and cheaper because of the easier technology to manufacture permanent magnets and all those things, right? So you see that brassless DC motors are actually one sort of permanent magnet motors where we can have a rotor inside or rotor outside, right? Now the basic advantage is that, right, that rotor is actually carrying permanent magnets having no coils, and since that and because of that, the efficiency jumps to a very high value automatically. It is about say 95 to 98%. And not only that, they have got higher starting torques and higher say torque to weight ratio compared to most of the other machines, compared to most of the available other machines that I am saying. Okay, so they are gaining increasing popularity, right? So it has been written here, high torque to weight ratio. That means motor weight and torque. If you compare, take the ratio, it is high for BLDC motors. So the last point you note, the BLDC motors are the most preferred motors for the electric vehicle application due to its traction characteristics, not only traction characteristics, its other various characteristics, I can say. Now, BLDC motors, we'll discuss a little more, have two types, for EV applications, have two types that I have said. The first one is outrunner type BLDC motor, outrunner type. So in this type, this is other name is hub motor. Outrunner means rotor is in the outside, hub motor. So electric bike, if you see, electric bike or electric scooter, if you see, that outer surface that is rotating. So inside part is stationary, right? So this type of motors does not require any external gear. It can be directly coupled. It can be directly mounted on the wheels. Okay. Now these are less bulk. I'll show you the picture first. This one. So this is outer rotor machine. So if you see that the permanent magnets are this one, red and blue one, they are being sticked or they are being pasted in the inside the rotor part, and the outer part is rotating. Okay, outer part is rotating, having permanent magnet. So inner part is having the shaft fixed and the rotor. So we have got slots, as I am showing through the arrows. and there we can place the windings. So we can have three-phase windings and as many number of poles as that of rotors. Okay, and then then come back to the point. Now these have got less bulkier structure because the lightweight, because of lightweight of the permanent magnets. Rotor is having lightweight, very lightweight. Permanent magnets nowadays are manufactured from say rare earth elements, NDFE, BM or like that. So they are actually having lesser weight but higher flux densities. Okay, and the space requirement for mounting the motors, they are also eliminated. So the application has been listed down in the bottom. Electric cycle and scooter applications. This is the picture, and this is the hub motor view. So I think a lot of you, I think almost all of you have seen this electric bike, say wheels like this. Okay, so the outer part is the rotor and inner part is the stator, and then that is fixed like that. Okay, so this. Now the second one is in-runner type BLDC motor, in-runner type. Now in this type, the rotor of the motor is present inside and the stator is outside, like conventional motors. This is like conventional motors. Now here we have rotor inside and stator outside. Now naturally, when stator is outside, so rotor has to rotate. So some sort of transmission system has to be there, power transmission system from the rotor shaft to the body, right? Now this configuration is bulkier as because of the transmission system is required, and at the same time, say the motor size. You see that rating of the motors usually larger than the outrunner type motors. Now, many three-wheeler manufacturers use this BLDC motors. Three-wheelers means auto rickshaw and all. Now, these are low and medium performance scooter manufacturers. They are also using these BLDC motors for propulsion. And these are widely preferred for electric vehicle application. Now, the drawback for both these machines, permanent magnet machines, as I have said, overloading the motor beyond a certain limit. Now, if you overload the motor, so beyond a certain limit means the armature is carrying larger current. So it produces demagnetizing ampere turns actually, right? Now, this demagnetizing ampere turns actually tries to oppose the flux produced by the permanent magnets, and they will try to demagnetize. Now, for regular usage, regular high loading usage may demagnetize the machine after some span of 3 years, 4 years, 5 years, depending on the conditions. Okay. Now you see, these are the structure. This is, again, there are two types. One is surface mounted, that is SPM, permanent magnet machine, and then interior permanent magnet machines, IPM, SPM and IPM, surface mounted permanent magnet and interior permanent magnet. So surface mounted means we have rotor, and on the rotor surface you see the magnets are shown here. That means in red and blue we are showing, and outside there are stators, and we have stator slots inside which there will be windings. The 4-pole machines are shown here actually. Okay. So now you see this is the picture of the BLDC motor having say in-runner type, right? This is a 48 volt 10 kilowatt machines. So 48 to 96 means there are various coils. It can be used at different voltages. So nowadays, manufacturers are flexible, so they do not know what type of usage are there. So there are coils. So we can have series parallel combinations for the coils. So now this is the torque transmission system. So here this is the wheel, and then we have got say some kind of say belt arrangement with gear belt arrangement, right? So geared belt arrangement. So this is the motor top, and there are say reducers, you can say. It runs at high speed, and the speed reducers are there, and then ultimately it is driving. So it is, I mean, the picture is from an auto rickshaw engine. So this is like that. Now inner rotor or interior permanent magnet machines are like this. So we have got rotor structure only, this one. So the rotor actually is having permanent magnets inside the rotor. That means they're mounted like this inside, not on the surface, inside. Okay. So there are specific advantages and disadvantages of both these types. So we are not going into that, but you should learn actually these are the basic types of the motors that are existing for BLDC machines. Now the third category is permanent magnet type synchronous machines, PMSM. Now this motor is similar to BLDC motor, but it has got also permanent magnets on the rotor. But the thing is that its back EMF waveform, or rather its EMF waveform, is sinusoidal compared to what I have said, the BLDC having trapezoidal waveform, right? Now, since it is sinusoidal, so the control techniques little bit conventional techniques. For BLDC machines, since actually it is trapezoidal, so if you try to apply normal DQ reference frame theory and then analyze the machine and then have it some control technique applicable, so that becomes a little bit difficult because there the basic waveform is different. Okay, so there are different approaches, there are various approaches, different approaches. Say even that is having a higher computational requirement for the processors are there, but the machine is really rugged and widely applied, you can say. Now, see, here is the back EMF waveform for the PMSM machine. Now this is the back EMF waveform for the BLDC machine. So these are differing from the basic point of view. Okay. Now the permanent magnet synchronous motors are having relatively higher ratings. Permanent magnet synchronous motors, PMSMs, are having relatively higher ratings. That means they are used in the drive systems where larger rating motors are required, like say buses, even say big cars, right? So PMSM is the best choice for, it has been written here, is the best choice for high performance applications, rather high performance and high wattage applications, high power applications like cars and buses. Okay. Now, despite higher cost, PMSM is providing stiff challenge to the induction motors due to increased efficiency than the latter. Now, why efficiency is higher? Again, you see that PMSM, as you see by name, the rotor is having permanent magnet. So rotor is carrying no coil. So therefore, no copper loss, right? So now if the machine is almost operating at synchronous speed, most of the cases, except from transient situations, but as I know that the transient situation exists, I mean, almost all the time during, say, during driving a car. But still, if you see, even the transient is there, so the difference of speed between the rotor and the stator flux is quite less. So therefore, actually, the core loss occurring in the rotor will be also minimized. So the rotor will be having almost negligible losses. Whereas in the induction machine, rotor is having copper losses, high copper losses, because rotor current, we can say, is almost equal to stator current. So therefore, copper losses are going to exist. And although the slip is less for induction machines, so you see that the rotor core loss will reduce. But again, during braking operations, reversal operations, so always we'll have high core losses within the rotor. So compared to this two machines, induction machines will be incurring higher losses compared to the permanent magnet synchronous machine. So that is why it is gaining more and more importance, right? So then PMSM, as I said, it is costlier than BLDC motors, and its rating is also higher. Most of the automotive manufacturers use PMSM motors for their hybrid and electric vehicles. Now, if you see that some examples we have given, Toyota, Prius, and then Chevrolet, Ford, various companies, they are Nissan, the BMW, they are all having some research work or some already established system with PMSM motors for propulsion, and they are reliable also. So, okay. So this is what inside view and all that you can see from various books. Now the fourth one is actually the three-phase AC induction motors. Three-phase AC induction motors. Now the induction motors, as you see, do not have inherent high starting torque. Do not have inherent high starting torque like DC series motors. But actually, with the help of modern control technique, we can use this to have a high starting torque. With the use of modern control technique, we can actually operate them at higher starting torque. Right now, what are the techniques? So you know actually FOC field-oriented control method. So that can easily impart a high starting torque or high torque during starting. Or V/F control, you see that low frequency operation starts with higher torque values. If you remember the characteristics, of the V/F controls at lower frequencies, you see that the starting torque gradually increasing because of the, I am not analyzing it. You can analyze yourself why it is. It can be analyzed easily from the motor equivalent circuit. So then, instead of having, even though we are having lower starting torque, but the induction motors can be easily made available for higher starting torque applications. Now, the maximum torque is made available at the starting of the motor is suitable for traction, right? Squirrel cage. Now, here, the major advantage here. Now, the cage motors are having more ruggedness compared to even PMSM. Nowadays, PMSMs are also having rugged, but that problem is still existing of demagnetization. But nowadays, I am saying that modern control techniques has been widely applied for those machines, PMSMs, so that the demagnetizing component of fluxes, they are getting reduced. So we can have FOC with PMSM drives. We can have direct torque control with PMSM drives, and then operate it in such a way that demagnetizing portion is less or not existing at all. But anyway, there are scopes of demagnetizing ampere turns appearing from the stator side. So therefore, to that extent, squirrel cage induction motor is having more rugged and longer life. Having more ruggedness and longer life compared to the PMSM. And its efficiency is little less, lying between 92 to 95%. 95% a little bit optimistic for very large motors. But usually we get 90 to 93% to be very common. 90 to 93% to be very common. So we get. But the thing is that if you compare induction machine and a drive system, right? Induction machine and a drive system, BLDC machine and a drive system, right? So BLDC motor having, say, an efficiency of, say, 98%. Now the drive system, if you consider for BLDC and induction machine, so comparatively induction machine drive systems will have a little better efficiency. Now the overall efficiency is the multiplication of both the efficiencies, right? Say 0.98 into 0.95, right, is equivalent to 0.93 into 0.95 or 0.93 into 0.96, like that. So therefore, overall efficiency is almost will be differing by almost say one or less than 1%. But still, that matters, because you see that whenever the motor drive rating is increasing, say for a 30 kilowatt machine, right? So 1% efficiency is how much? 30 kilowatt, say 0.3 kilowatt, 300 watt. It is not a matter of say negligence. It's not a matter of negligibility, you can say. 300 watt is quite good. So that is why that going towards better efficiency is always expected. Now this I'm not going into details the induction machine. Drawback in the inverter circuit and most difficult and all those things. Now we'll end up this this motor part with some say conclusions, means which motor to operate when, right? Now see, this also I will skip. Reducing the losses improves efficiency, that's all. Okay, now this is okay. Now, right. Now, induction motors, you see, induction motors are having their usage in bus drives. So, like the red, I have mentioned that the Tata Motors, they are using induction motors for their buses, right? And TVS Motors, two-wheelers, they are also trying or induction motors, right? So now the choice of the motors. Now, if you see that, say there are certain constraints we should have. Like say, first of all, what do you try to, which element you want to compromise or which one element you want to stress upon. Like say, if you want a lower cost thing, induction motors are the preferred choices for medium sized to higher sized vehicles. When cost is the consideration, cheaper in cost, right? And ruggedness, right? Ruggedness. Now, if you want to have some lower rated motors, if you want to have some lower, oh, I have sorry, I could not, I have missed this part, switch reluctance machine. So that this part I complete and then I will discuss. Okay. So the fifth type of motor is actually, because it is extending, so I am trying to shorten them up. So that is why I thought that this slide is discussing the selection of the motors. It is not that. Switch reluctance, SRM. The fifth motors are actually switch reluctance. So this is also actually gaining importance. So this has got another bigger advantage, is that the rotor is having neither magnet nor any winding. The rotor is having neither magnet nor any winding. So then the chances of demagnetization is not there. Okay. And no winding means actually there is no copper losses, right? And then it almost runs behind the main flux. So the copper losses, core losses are in the rotor are also reduced. That means these motors will be becoming, I mean, the major challenge for the other motors to exist, provided a very suitable drive system is designed. So nowadays, the switch reluctance motor drive systems are not that rugged or reliable under all conditions. Okay, so I mean, those who will be doing some research, they can find out some topic on this switch reluctance motor drive system for this vehicular drives. So that is becoming, I mean, a hot topic these days. Okay. But still, I mean, some people have already left it because they have thought that, that switch reluctance motors are not, I mean, that much of having that much of prospect compared to this induction or say PMSN counterpart. So now, simple in construction and robust, inertia of the rotor is less, which helps in high acceleration. So it is very suitable for high-speed applications. It is having high power density. All the advantages are having. It is easier to cool the motors because the rotor is having some grooves already, and that creates a lot of air in the stators. It also has some noise. It has some noise issues because of the saliency in the rotors. right? So once SRM enters the commercial market, it can replace the PMSM or induction motors in future. So this is the futuristic comment I have made or scientists are making, but the drive system is still yet to be very highly proven. Okay. So then this is the pictorial view of SRM. Now this is the basic construction that you know, you have studied in your year. There's a rotor as a 4x6 structure. Now we have insights for selecting the right motors. That is what I was telling. Yeah, insight for selecting the right motors. Now the operating conditions and the cost, that will be the deciding factor, as I was talking earlier. Operating condition and the cost. These two are the most driving factors for this selection. Now, for example, if you want to have a two-wheeler application, with less than 3 kilowatt, with motors capacity having less than 3 kilowatt, it is best to have BLDC hub motors. Because as I have said, while in the course of the lecture, I have said that the hub motors, they can be easily designed for low capacity, below 3 kilowatt, below 1 kilowatt, like that. Okay. Now for three-wheelers and two-wheelers, they can also choose BLDC motors with or without an external gear, because for three-wheelers or two-wheelers also the motor capacity lies within, say, 5 to 7.5 kilowatt. So I mean 7.5 kilowatt is a little bit high for the hub motors, but for the normal motors, inner rotor motors, I mean it is good. That means still BLDC motors can be chosen, I mean at low cost. Now for high power applications, if you have high power applications like say two-wheelers, cars, buses, trucks, the ideal motor choice should be either PMSM or induction motors. So that you should think of. And nowadays, of course, SRM is also coming. So this is the end of the motor session. So now we will go slowly to the drive system and then discuss slowly that configurations of the things. So just I will take some, say, little 2 minutes break. I drink some water and then come back. Yeah, okay.
I will join after 2 minutes. Okay.
So, okay. So, good afternoon. I'm back. So,
Welcome back, sir.
everybody is okay. Means I can start.
Yes, sir. Yes, sir. Yes, sir.
Okay. So now, see, this is the basic block diagram of an electric vehicle powertrain. That means how that power that is converted to say drive the electric vehicular motors. Now here from the left side you see we have grid system, right? Now grid system, as I said, that it's onboard charger. So from here, from this green box, you just consider the right side. Okay, so this part actually will not discuss. So what we discuss is the inside part only. So then here you see that this charger is charging a battery, and this battery is our source at this moment, let us say. So I'm using the arrow, right? The propulsion battery is the source. Now, the most of the converter systems or most of the drive systems is having one internal DC bus, right? Now, this DC bus is created from the say low power battery, low voltage battery. The batteries are having usually lower voltage, say 12 volt or say even maximum 24 volt like that. So now after that, actually, higher voltage DC bus is created with the help of DC-DC converters, boost converters, right? Usually boost converters. So now the other source is shown here on the top, which is actually a supercapacitor. So supercapacitor, you know, a capacitor having high capacity, very high capacity. So these are meant to absorb or deliver instantaneous power, instantaneous energy to the system. Means batteries actually usually have got a limited rate of charge and charging and discharging, right? Charging and discharging both. So now it can so happen the motor breaks very fast. Now what happens? The energy is to be extracted fast. So the battery may not be able to absorb that energy at that faster rate. So that is why supercapacitor is used, and this common high voltage DC bus, HVDC bus, HVDC high voltage means actually compared to the battery or the supercapacitor voltages, the DC bus voltage is higher because it will be driving the motors. Because if it is an induction machine, the capacity is usually at 110 volt. So for 24 volt DC bus, it is difficult for an inverter to operate at 110 volt AC. So therefore, you have to boost it up to a voltage near to that voltage and then convert it to the converters. Now, there is another conversion system is there from the HVDC bus. There is one Lvdc to DC. Now, Lvdc to DC, what is that? It is meant for supplying the auxiliaries, like say horn, like say light, like say your processor, right? So who will supply? That HVDC bus will not be able to supply. A direct battery also will not be able to supply because the processors will need 3 volts, right? Or 5 volts. And lights may need 6.5, 7 volts, depending on the voltage ratings. So this Lvdc bus actually will be driving the auxiliaries, right? And there actually another battery is shown, which is auxiliary battery. Auxiliary battery. Now this auxiliary battery, for a big system, there are 2 batteries. For main propulsion battery and auxiliary battery. So auxiliary battery is meant for the auxiliary system. So this is the driving system. Okay, so then our discussion will be on mainly 2, then DC-DC converter and the inverter. DC-DC converter and the inverter. So these 2. So then actually, again, if we look at the configurations, this is the same thing. What I said is something this electric motor generator, traction inverter. It is supplied from inverter, and then we have a DC-DC converter, and then AC to DC converter. This is charger, the charging spot, and all the same in block diagram has been mentioned here. So this also classification of the converter, these are all cookies type of thing. Now we'll get the boost converter techniques, boost converting techniques. Okay. So now you see that first topology that was tried was actually normal DC to DC boost converter. This configuration everybody knows, so I need not have to discuss. So what is happening now? This battery is having lower voltage, so we should have a higher DC bus, higher voltage DC bus. So this boost converter can be used. But the problem is that the first point you look at, the moderate voltage gain here with the help of boost converters, the voltage gain is always within 400%. Otherwise, stability issues arise, and then the device stress and all that increases voltage and current stresses. So all these things limit this topology to a say upliftment of voltage within 400%. Now efficiency is also very less, moderate. So I mean within 85%, within 83 to 85%. Okay. Now again the output voltage is, but the advantage is that the cost is lower. The cost for this type of converters is lower and simple in construction. They will consume lesser spaces, etc. Okay. And drawbacks, you see that the drawbacks, the larger capacitor to reduce voltage ripples, because here we are having higher voltage ripple, so capacitor requirement is high, and weight moderately heavy. So voltage gain is not possible. That's what I'm saying. For 24 volt, so if we have 110 volt, so actually what will happen? At least we have to increase it by 5 to 5.5 times in order to have a 110 volt motor being driven safely. So then this type of converter will not be, I mean, sufficient enough. So we have to think of something else. Now, parallel arrangement for power switching, I mean, not very high power also, suitable for a power of, say, less than 10 kilowatt, right? Parallel arrangement of power switching devices are required for high power. Extra stages are required for short circuit protection schemes. So these are the drawbacks for this kind of system. So now, in order to remove it, the second generation of this boost converter came, which is actually interleaved boost converter, interleaved type, interleaved. So interleaved, sometimes coupled, cross-coupled interleaved are there, but here we have not shown it. There are various things existing in the research papers. So you can find out anyone and get your research done, but or research topic found out. But the suitable choice is also necessary where you can prosper better. So you will have n number of converter configurations. So I am not going to discuss all of them, but few of them which are very, very popular that I'll be discussing. So then this is interleaved means what is going to happen. Now we have 4 such legs. Now in earlier we had only single leg here. Now 4 legs means they can be switched at 1/4 of the frequencies. If we want to have same frequency at the same ripple frequency at this terminal, at this end, at the output capacitor terminal. So then what will happen when the frequency is reduced actually the losses also will reduce, and you can have inductor sizes that can be also reduced. But actually what will happen if you use same frequency 4 times the output frequency, and ultimately the capacitor size will reduce. So all these things actually make it popular, although the switch count is higher, but overall we are having a better operation. Now I am giving some figure from one of our papers regarding this operation to understand. Like say only I have shown 2 legs. So now say for the switch 1, this is the operating cycle, and switch 2 is operating just in opposition. Means when this is on, this is off. When this is off, this is on. Thus they are mutually exclusive. And ultimately that delta IL1 is rising when it's on and falling when it's off. Similarly, this is Now, when you see the total current, I output current, right? I output current. So rather, I see out capacitor current. So now they are having double the frequency of this switching frequency, right? So therefore, your capacitor rating can easily reduce, right? Now the current I1 and I2 will be like this, and then if you add them up, you can get this current. You can get I output plus IC out. Now I output is a DC current. If you subtract DC average value, you get this one. Okay. So this way, I1 plus I2 minus I out. This way. So this is the thing. So now by use of this, input inductor and output capacitor size can be reduced. And frequency of input current ripple is n times higher than the switching frequency. So that will actually, how that will help? That will help to decrease the filter components, decrease the rating of the filter components. Now here you see efficiency. That was 85% earlier, at the most 85, 86%. Now we have been able to achieve around 92% for a 30 kilowatt rating. I mean, bigger. So these are actually useful for high power applications. That was single was actually less than 10 kilowatt. So this can be used for high power applications. Now again, to have some further advancement, so we can have boost type of DC-DC converter with resonant circuit. Now how does it help? Now this actually, as I have said, there are switching of the devices. So naturally the switching losses that count actually, that actually reduces the efficiency of the converters. Now you see that here, that the first MOSFET Q1, the first MOSFET Q1 is the main switch, main MOSFET, and Q2 is the actually the auxiliary MOSFET. Now, if you look at the circuit, so this DC voltage, this inductor, and this capacitor form a tank circuit, and then the resultant current is a sinusoidal one, and this Q1 can be easily switched on when the voltage across the capacitor is 0. Okay, so then ZVS switching is achievable for Q1, right? And similarly, if you see this capacitor voltage, this inductor, capacitor, and this switch, or on the other hand, this battery, this inductor, and this capacitor, this switch, they can form one tank circuit. Okay, so that will create a sinusoidal current. So therefore, at current 0, this Q2 can be switched on, right? So then the ZVS can be achieved for Q1 and ZCS can be achieved for Q2. And in this way, actually, switching losses can reduce. Short switching characteristics reduces the size and weight of the converter. And with the help of this, switching frequency also can be increased. Now, when switching frequency is increased, so automatically the size of the components that can reduce inductors and capacitors. Now, but this thing, as we know, that the short switching is actually a switching which has to operate at a specific interval of time. A small period of mismatch can lead to, say, other voltage stresses and current stresses across the devices. So to avoid that, normally this type of converters are not designed for very high rating. So usually suitable there for less than 5 kilowatt system, but at high frequency, very compact. And the output voltage gain of greater than 400% is still not possible. Bidirectionality cannot be achieved. So nowadays, bidirectionality is a fact, because you know that the battery has to receive power sometimes when it is, say, regenerating. So those things are also to be taken care of. But still, they're step-by-step developments for the converter system. Now, the fourth one is the full bridge boost type DC-DC converter. Acha, excuse me. So I think the time I have, reached what the slot you have given me. So up to five. So I will end up with this one, and from the next one,
Yes, sir.
probably I will catch up tomorrow. So
Yes, sir. Yes, sir.
in the morning. Otherwise, the times management will not be
Yes,
there
sir.
from
Yes,
my
sir.
side. Okay. So
Yes, sir. So do you have, so participants, you have any query? You can ask sir now, or you can ask tomorrow also, because tomorrow in the morning also sir is having the session.
So I have not given part one, part two. So this slide I end up. So here you see, just this I describe and finish. So here you see a full bridge type boost converter. So here these two switches Q1, Q2, Q3, and Q4 will act as a boosting type of thing, and then the transformer is there for energy transfer. So there also we can have a voltage ratio, higher voltage ratio. Right. So then actually this is suitable for higher ratings. This is suitable for higher ratings, and power transfer to the motor is, at a larger rate. So more than 30 kilowatt or 30 kilowatt rating, and at a considerable efficiency. We can have higher switching frequencies here. Okay. So, so this configuration I end up. So participants, please, if you have any questions, please come forward. So I will be trying to answer in next 5 minutes. So after that, I will end up this session, and then we'll start tomorrow. Yeah.
So you have any queries, you can ask sir now, or sir is having session tomorrow morning also.
Tomorrow morning at 10 p.m. 10 a.m.
Sir, I will have to check sir once, and then after I will inform you, sir.
I think
Okay, sir.
it starts at 10. It starts at 10.
Yes.
I think it is 10.
11 a.m. sir. It starts at 11 a.m. sir. But
11.
if you
Just,
are
oh,
yes,
then I will get to know. I will get check the mail and then accordingly start.
yes, sir.
Okay.
Yes, sir. Yes, sir. But if you okay, okay, sir.
All right.
So I would like to thank Professor Debashis sir to be present here and answer to all the queries. I would also like to thank the participants for their kind patience and the kind participation. And most probably this was the this is a session full of technical things. I mean, it was the best session, I would say. From my side, it was really very nice session, sir. Okay, sir.
Okay, thank you. So
Thank you, sir.
thank you. So
Thank
we
you for
meet
being with
tomorrow
us.
then. We meet
Yes,
tomorrow
sir.
at
Yes,
the
sir.
stipulated time. Okay. Okay. Thank you.
Yes, yes. Thank you, sir. Thank you.
Oh, thank you.
স্যার টুমরো কি আপনার পেশেন্ট আছে 10টা থেকে আছে স্যার কালকে
10টা তাই তো আমার সেটাই
হ্যাঁ,
মনে
স্যার,
পড়ছে
হ্যাঁ,
10টা।
হ্যাঁ স্যার হ্যাঁ স্যার হ্যাঁ স্যার 10টা থেকে আছে স্যার
ওকে, অলরাইট।
থ্যাংক ইউ স্যার থ্যাংক
ওকে,
ইউ
থ্যাংক ইউ।
ভেরি
থ্যাংক
মাচ
ইউ।
স্যার
ওকে, ওকে। আই লিভ।
ইয়েস স্যার ইয়েস স্যার ডেফিনেটলি
ওকে,
স্যার
আমি একবার ভিডিওতেও তোমাকে দেখে দিলাম। ওকে। তো
এক সেকেন্ড একবার জাস্ট ভিডিওটা অন করে রাখুন স্যার ওকে আই উইল লাইক টু রিকোয়েস্ট অল দ্য পার্টিসিপেন্টস অলসো to means switch on their cameras so that I can take a snapshot. Participants, please switch on your cameras once. এক second, sir, na. 2 minutes just, sir.
ওকে, ওকে।
Everyone, please switch on your cameras so that I can take a snapshot of this session. Thank you, sir. Very good, sir. Very good, sir.
Okay. All right.
Thank you, sir. Thank you, sir.
So I leave. I leave it.
Yes, sir. Yes, sir. Yes, sir. Definitely, sir. Definitely, sir. Okay, so dear participants, as far as my knowledge goes, this session was full of technical things actually, and it was most probably the best session all over, I would say, because so many technical things were involved over here. So tomorrow we are having again Professor Debashis Chatterjee with us. Okay, and most probably the session will start by 10 a.m. I feel. Okay, so I'll send you the link again, and the slides, the presentation will be shared to you at the end of the workshop. Okay, because the faculty is there, means they will have to send the PPTs to me and all. Okay, so when I receive all the PPTs from the concerned faculty members, I will definitely, forward it. Fine, now.
Yes, sir.
Thank you for being with us. Thank you for being so patient. But this
Dr.
session.
Shantanu, what about attendance link for this?